In this video, we're going to talk about whether a molecule is polar or nonpolar. So we've previously looked at covalent bonds, and we said covalent bonds could be polar or nonpolar. If there was no electronegativity difference, those electrons are shared unequally between the two atoms in the bond, and we have a polar covalent bond. If the bonding electrons are equally shared, then it's a nonpolar covalent bond. What we're going to do in this video is extend that concept to the entire molecule. So molecules can also be polar or nonpolar. And this is actually a pretty comprehensive topic. What we need to be able to do is draw the Lewis structure, determine the molecular geometry, assign bond dipoles, and then look to see if those bond dipoles are going to cancel each other out or sum together. So nonpolar molecules, we can actually get these two different ways. So first way, all bonds are nonpolar. So if you don't have any polar bonds, you cannot have a polar molecule. So if all of your bonds are nonpolar, your molecule is going to be nonpolar. Our other option is you have polar bonds, but they're arranged symmetrically. And they cancel each other out. I shouldn't say and, because they're arranged symmetrically, they cancel each other out. And I will draw some structures so you can see an example of this. Polar molecules, these are going to have polar bonds. Again, if it doesn't have a polar bond, it can't be polar. So this is going to have polar bonds, but they're arranged unsymmetrically. They actually do not cancel each other out, but sum together. So we have polar bonds that are arranged unsymmetrically. They do not cancel. And actually they sum together. So I think the easiest way to see this is to draw some examples. Again, it's pretty cumulative, so what you need to do, I'll just make a little list here, is you need to draw the Lewis structure. You need to determine and draw the molecular geometry. It's really important that you do the next step on the shape of the molecule, its three-dimensional shape, and not on the Lewis structure. The only reason we're drawing the Lewis structure is so we can figure out how many electron groups we have. Once we figure out the number of electron groups, then everything is going to be based on the shape of that molecule, right? The three-dimensional shape. We're going to assign bond dipoles. I might not have used the term dipole before. When I say assign bond dipoles, we're saying assign polar bonds. So if something has a dipole, it's polar. Right, di means two, so it has two poles, it has two ends, right? A partial positive end and our partial negative end. So when I say assign bond dipoles, what I'm really saying is assign polar bonds. So use delta notation, find out the partial positive, partial negatives, add your arrows, right? Let's actually add to that. Assign polar bonds using delta notation. And then number 4 are the bond dipoles. Arrange symmetrically, right? Do they cancel each other out, or not symmetrically, unsymmetrically? Do they not cancel each other out? And again, it's really important that when we're doing those bond dipoles, you do it with the shape of the molecule, the three-dimensional shape, and not the Lewis structure. And I can do an example where you would get the wrong answer if you do it on the Lewis structure. So this has to be on the molecular geometry, the ones with the wedges and the dashes, right? The shape matters. We're looking to see if they're arranged symmetrically, which means we need to know what the molecule actually looks like, right? Not what it's necessarily just connected to, but how are those things oriented in space? So some examples. Carbon dioxide, we've drawn this one a couple times, so I'm just going to jump right to the shape. Carbon dioxide is linear. So I do have 180 degree bond angles between here and here. So this is linear, just in a straight line. So this is my molecular geometry. I know that carbon-oxygen bonds are polar, right? Remember our nonpolar bonds. We're going to be something bonded to itself, carbon and hydrogen, phosphorus and hydrogen, and carbon and phosphorus. Again, there are others, but this is the list I'm going to stick to. Carbon, oxygen are not on that list, so these are polar. Oxygen's more electronegative, so it gets the partial negative. Carbon gets the partial positive, and then those electrons are being pulled in that direction. I have another carbon-oxygen bond on the other side. So oxygen's still more electronegative than carbon. So those are being pulled 180 degrees, right, in the opposite direction of the others. So it's kind of like, and these do have numbers, I'm just making up numbers, but if like this was a 7, then this was a -7 because it's the complete opposite direction, and they would cancel each other out, right? My 7 and my -7 would cancel. So this is actually a non-polar molecule. I have two polar bonds, right? I have one here and one here, but they're symmetrical. They're going to cancel each other out. So my molecule itself is nonpolar. So this is a nonpolar molecule because it's just one. I'm going to compare, let's do CH4, CF4, and then CF3H. So all three of these have carbon in the middle. If you were to draw the Lewis dot structure, for the first one I have carbon bonded to 4 hydrogen. On the second one, carbon bonded to 4 fluorine. All of those fluorines have 3 lone pairs, but that doesn't affect my shape, right? My shape is going to be tetrahedral because I have 4 bonds and no lone pairs. And then my last one, carbon bonded to 3 fluorines and 1 hydrogen. It doesn't matter where I put the hydrogen, I just replace one of them. So all of these are going to be tetrahedral, right? They all have carbon in the middle. They're all bonded to 4 things. No lone pairs on my central atom. So I'm going to just go right to drawing my geometry. So carbon going to hydrogen. Remember, something's tetrahedral. We have 2 in the plane, and then we have 1 coming out at us. That's that wedge, and 1 going back. And then I'm going to draw essentially the same thing, but I'm going to have fluorines instead of hydrogens. And then 1 more. I can put the hydrogen in any of those spots. I'm going to put it on the top, but one of the 4 spots, it really doesn't matter which, is going to have that hydrogen. Oop, that's supposed to be a fluorine. Okay, so I kind of skipped through the Lewis structure, but we drew the Lewis structure, then we drew the geometry. Our next step is to assign polar bonds. And if I look at this first one, CH4, all I have is carbon-hydrogen bonds. And if we go back up to our list, carbon-hydrogen bonds are on my nonpolar list. So this molecule itself is a nonpolar molecule. And my reason for that is I don't have any polar bonds, right? If we go back up, one of the ways we can get a nonpolar molecule is that all bonds are nonpolar. And that's the case here. So I have 4 carbon-hydrogen bonds. All of those bonds are nonpolar, so my molecule is nonpolar. My steps assign bond dipoles. I'm not going to do that to this one because I don't have any, right? My dipolar, my polar bonds, I don't have any polar bonds. So this one's just plain nonpolar. Assigning bond dipoles to my carbon tetrafluoride molecule, fluorine is more electronegative than carbon. So those get the partial negatives, carbon gets the partial positive. And then my arrows. So this one is actually also a nonpolar molecule, but for a different reason. All 4 of those are arranged symmetrically. They're going to cancel each other out. And it might be kind of hard to see, but I like to think of this kind of in groups of 2. So like these 2 are canceling with those 2. Sometimes I like to think if we were, if you can visualize it, if I have carbon in the center, and then I'm going to essentially tie 4 strings to it. So let's say I just take an object, it doesn't matter what it is, and I'm going to tie 4 strings. And I'm going to pull straight up with one of those strings. So I guess 4 different people I'm going to give strings to. One's going to pull straight up. One's going to pull in this direction. Remember, this is in the plane. One's going to pull out, and one's going to pull back. And everyone's pulling with the same strength. When I let go of that object that the string is attached to, what's going to happen to it? Is it just going to hover there, or is it going to move in some direction? Good. Yeah, it's just going to hover there, right? All of these are pulling with the same strength, right? This person's pulling angled out with the same strength that this person's pulling angled back with the same strength that those are pulling. So when I let go of that object in the middle, it's not going anywhere, right? So they're symmetrical, they're canceling each other out. If I look at my next one, fluorine's still more electronegative than carbon. Carbon-hydrogen bonds are still nonpolar. So when I look at this one, I only have those 3 bond dipoles. So I don't have one going out. So kind of going back to this middle one, right, with the 4 strings, this person's pulling, this person's pulling, this person's pulling, this person's pulling, and then the person on the top lets go of their string, right? That one's no longer polar. What's going to happen to that object that they're tied to? Yeah, it's going to move, right? It's all going to kind of move down. Remember that these are angled down, right? This is going down, this is coming down and out at us, and then down behind. So if we're not pulling up with the same amount of strength, when I let go of that, it's going to go down. So this is actually going to be a polar molecule. I have polar bonds, but they're unsymmetrically arranged, right? I don't have something, they're not canceling each other out. I'm just going back and fixing this one for you guys because it looks pretty horrible at this point. So kind of all 3 examples, right? I have a nonpolar molecule because I don't have polar bonds. I have a nonpolar molecule that has polar bonds, but they're symmetrically arranged, they cancel each other out. And then I have a polar molecule. It actually has polar bonds and 1 nonpolar bond. Those 3 polar bonds are canceling each other out. Remember the shape of that. The shape's important, right? It's shaped like a little pyramid. So this is coming out at us. And then this one's going back. It's supposed to be arrows in the plane, right? Nothing's going up. So the whole thing is going to kind of pull down. So polar. I said I would do an example where if you just do the Lewis structure, you might get the wrong answer. And water is a really typical example. If I draw the Lewis structure for water going through the rules, 6 electrons for oxygen, 1 for each hydrogen. I have 2 of them. Oop, I'm jumping ahead. It's going to be 8 total. And then using my rules, I put oxygen in the middle, and then I tend to make things symmetrical. And then I can't put any lone pairs on my outside atoms because they're hydrogen. I have 4 left over, so 2 lone pairs on oxygen. So this is my Lewis structure. If I was to go and assign bond dipoles to this, oxygen's more electronegative than hydrogen. So I have one going in this direction and one going in the complete opposite direction. Again, it's like if this was 7, and I'm just picking a number, this was -7, right? They would sum together to cancel each other out, right? They would sum to 0. So if I do it this way, I would actually say nonpolar. I would say that water is a nonpolar molecule if I assigned bond dipoles to this Lewis structure. However, I would be completely and absolutely wrong. Water is polar. This is incorrect. And our reason for that is that water is not linear, right? In this structure, I drew water as linear, and water is not linear. Water is bent, right? I have 4 electron groups, 2 bonds, 2 lone pairs, and my 4 electron groups, again, are that basic tetrahedral structure. So I can put the 2 lone pairs any place I want, but I'm going to choose to put them coming in and out, and I'm actually just going to kind of ignore them for clarity. So what I'm going to do is I'm going to put a hydrogen here and then a hydrogen here. So I'm going to go up to a hydrogen and then a hydrogen. And then I would have, right, my lone pairs. I'm just going to leave them off to make the picture not quite so like easier to look at. Now when I assign my bond dipoles, right, those do not cancel each other out. They're actually angled, right? So I now have a polar molecule. Which is correct. Water is polar. So again, be really careful when you assign those bond dipoles. It needs to be on the shape of the molecule, right? The 3-dimensional shape, the molecular geometry. If you do it on its Lewis structure, you can get the wrong answer. So back up here, right, on the molecular geometry, the shape is really important. With water, right, we get a different answer. And again, you don't have to draw the Lewis structures the way that I do. If you drew the Lewis structure like this, now you're going to get the correct answer because it doesn't matter with Lewis structures, right? The shape, the Lewis structure has nothing to do with shape. So make sure when you assign those bond dipoles, you're doing it on the molecular geometry, right? You're not doing it on the Lewis structure. I want to go through another example. So let's do, how about SEBR4. So we're going to draw the Lewis structure. We're going to draw the molecular geometry. We can check for formal charge. It's always something good to do. And then we'll assign bond dipoles. We'll determine if the molecule is polar or non-polar. So I'm going to go through all the rules for this one. So Se is selenium. It's in group 6A, so that's how we're going to remember the number of valence electrons it has. Bromine is in 7A, so again, that's how we're going to remember it. Multiplied by 4 because there's 4 of them, so that's 28. 28 plus 6 is 34 electrons. I'm going to put selenium in the middle, and I'm going to bond it to my 4 bromines. I have lone pairs on all of these terminal atoms, so each gets an octet. My next rule says if I have electrons left over, they're going to go on the central atom, so let's count. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So I do have electrons left over. Let me get this out of the way here. And those lone pairs again are going to go on my central atom. So I'm going to put a lone pair somewhere on selenium. Again, this is just the Lewis structure, so the only thing that really matters is that selenium's in the middle. It has a lone pair and 4 bonds to bromine, and then each of those bromine atoms have 3 lone pairs on them. To figure out my molecular geometry, I'm going to look at the number of electron groups that I have on my central atom. So I have 1, 2, 3, 4, 5. And 5 is that basic trigonal bipyramidal structure, the one where we have the axial and the equatorial positions. I made that bond kind of long. That one's kind of short. I feel like Goldilocks now. So remember, if we have a lone pair, it's going to go in one of those equatorial positions. So the lone pair has to either go here or here or here. I'm going to use the one on the left, the one that's in the plane. And then selenium's going to go in the middle, and then I'm going to have bromine in my other spots. So SE, I'm going to go up to a bromine, down to a bromine, out to a bromine, back, and then my lone pair is going to be right here. I do have lone pairs on those guys. I'm going to put them there so we can check our formal charge real quick. This one doesn't have any, but it's good practice. So bromine, 7, right, is 7 valence electrons. And I'm going to count 1, 2, 3, 4, 5, 6, 7. So 7 minus 7 is 0. And all the bromines are like that. They all have 6 lone electrons and 1 bond. So none of them will have a charge. Selenium has 6 valence electrons. And if I count 1, 2, 3, 4, 5, 6, 6 minus 6 is 0. So no formal charge on that one either. I'm now going to assign my bond dipoles. Bromine is more electronegative than selenium is. So they're all going to get partial negatives, right? They get the greater share of those bonding electrons. Selenium gets a partial positive because it has the smaller share. So then these electrons are being pulled towards bromine. These are pulled towards bromine, and then pulled towards the last bromine. So what do you guys think? My selenium tetrabromide, is this going to be a polar molecule or a non-polar molecule? If you guys are thinking polar, you're correct. So for this basic shape to be non-polar, I would actually have to have another one going in this direction to counteract it, and I don't. If I was to draw, just kind of for comparison, PBr5, if I do that, I have phosphorus in the middle, it's bonded to 5 bromine, no lone pairs on phosphorus, 3 lone pairs on each bromine, so it's going to be the same trigonal bipyramidal shape. But this time, I'm actually going to have a bromine in all of my positions in no lone pairs. And it's not that there's a lone pair there, it's the fact that there isn't a bond there. I can have molecules that have lone pairs that are non-polar. So I don't want you to assume that just because there's a lone pair that it's polar. That's not going to be true. So if you're looking kind of for a shortcut, that's not going to work for you. So just watch out for that. So all my bromines here. And then my phosphorus. So you can kind of think about those two as canceling each other, right? We could do the same thing here, right? This one and this one cancel. And then on this one, I have 3 going around the middle. Let's actually do it in a different color. And they're forming essentially an equilateral triangle. So those 3 are going to cancel each other out also. The one up top, right? I have these 2, but I have nothing going in this direction. So that is going to be polar. This one here, that's a hard color to see. Non-polar. Right? I used the hard to see color here too. Sorry, guys. so nonpolar. Let's do one more. I actually have a good one for us. So pH3. So when we draw the Lewis structure for this one, I end up with a lone pair on phosphorus. So I have 4 electron groups. One is a bond. The other is, 3 are bonds. One is a lone pair. So I'm going to put the lone pair on the top position. So phosphorus in the middle. I'm going to put the lone pair here. You can put it in any of those spots. And then hydrogen, hydrogen, and hydrogen. And then remember, our next step was to assign bond dipoles. And that's where this one's kind of tricky. I don't have any bond dipoles. Remember, phosphorus and hydrogen have the same electronegativity, so nonpolar. The whole molecule is just considered nonpolar. I do have that lone pair, but the lone pair, if we went through our rules for doing it, isn't going to contribute, right? It does actually contribute a small amount, but overall, pH3 is considered a nonpolar molecule because I don't have polar bonds. Remember I said if I don't have polar bonds, it can't be polar. So when I had just said before about trying to use the presence of a lone pair kind of as a shortcut, don't do that, right? Here I have a nonpolar molecule and it has a lone pair, so do watch out for that. One more example for us. So let's use xenon tetrafluoride. And I'm just going to draw the Lewis structure. When we do this one, we end up with 4 bonds to fluoride. I have lone pairs on all of those. You would have first figured out your total number of valence electrons, and when you got to this point, you would find that you have 4 left over, so I'm going to put 2 lone pairs on xenon. When I go and draw my molecular geometry now, I have 6 electron groups, right? 1, 2, 3, 4, 5, 6. 2 are bonds, 2 are lone pairs. So this is going to be that octahedral shape. And then remember, if I have 2 lone pairs, they need to be opposite of each other. So what I'm going to do is I'm going to put one on top and one on the bottom. So xenon in the middle. And then it would go up to a lone pair, down to a lone pair. I'm going to draw the bonds first. So I'm going to come out to a fluorine. I'm going to go back to a fluorine. Back to another fluorine. This is that square planar shape. And then out to another fluorine. So that should be square. It helps to visualize it in 3 dimensions if I could draw better. But that's essentially what we're getting. And then I do have a lone pair here and a lone pair here. When I go and assign my bond dipoles, fluorine is my more electronegative atom. It is the most electronegative atom. So unless it's bonded to another fluorine, it will always be the partial negative. And then this one and this one, and this one and this one. So polar or nonpolar. Yeah, this one's nonpolar again. Right? And you can think about it. Remember, this is coming in and out of the plane, but these are linear, right? This one's coming, this one here is coming out, this one's going back, and they are straight across. And then this is linear, right? The whole entire molecule is square planar, but just the relationship between those. So we can think of this as canceling this, and then this one canceling this one, right? So these are going to cancel each other out, and the molecule is going to be nonpolar. It has 2 lone pairs, but again, that's not what we're considering. We need to consider the lone pairs when we figure out the shape, right? If I didn't have 2 lone pairs and it just had the 4 bonds, it would be tetrahedral, not square planar. But when you're assigning bond dipoles and looking for symmetry or not symmetry, right, we're just kind of ignoring those lone pairs.